discussion of the homework problem that was so confusing about the predictability time scale. So the slide that I have up right now is the discussion from his big book, not the Essentials book, but the longer book, which he thinks is the right way to think about it. So the key distinction from the homework problem is that it's not tau sub k, the time scale at a particular wave number, times the dk. It's tau sub k d log of k. So it's the logarithm. There's a logarithmic dependence on wave number, and the rationale for that is that it takes the same amount of time to move from k to twice k. That's what tau really describes. It doesn't describe for one particular k to move to k plus delta k, which would be dk there. So because it's a proportionality, so every time you want to double the wave number is what it takes to move a distance tau sub k. So that makes this integral a logarithmic one, so that proportionality is correct, which then means that this is the form, if you plug in for an arbitrary energy spectrum, and you can see that it goes like k to the 3 times e epsilon times the energy spectrum. So that if the energy spectrum goes like k to the minus 3, then you just get the integral of log k, which is an exceptional one. So this case, that the time scale for the transfer across all the logarithms goes like the log of the ratio. But if it's not equal to k over 3, I'm sorry, if e of k is not equal to k to the minus 3, why is this doing this? Then it goes like this other time scale. So in some sense, the key is that it's an exceptional case. The one case that is the epsilon of k goes like k to the minus 3 is the one exception. It's the singular exception to this particular scaling, and so that one is the one that becomes infinite. The rest do not. So here it is right here. This is the 2D result, and this is the 3D result. And so the 2D result goes like this logarithm, and so if k0 goes to, and so if depending on where you choose your outer limits of that cascade range, this is the result. And then for the 3D turbulence, it just depends on one of the two length scales, and so it doesn't become infinite. So I will update the answer key so that people can see this, but and I'll also put comments back. But I think people have struggled through this, so it'll be helpful to take a look at the answer key afterward. And I'll do the 50-kilometer case based on this scaling. Did anybody find this in thinking about it, or no? I mean, the key is that the equation that he gave us was incorrect because it didn't have the logarithmic dependence here. Okay, so Anna did find this correction. Good work.
I have an issue with this equation or this because it takes v ln k. But again, k is because I've been thinking about this. K is not k has some dimensions.
Right. So k has some dimensions, but if you take the difference because you're evaluating at two different locations, the answer doesn't have dimensions. So it becomes log of k1 minus log of k0 or log of k1 divided by k0. So yes, it appears to have dimensions when you write it this way, but because the integral works out to have a difference in it, the two limits actually end up being a ratio, which eliminates the limits from the result. Does that make sense? Yeah. So it's one of these peculiarities of the you could have guessed it. Well, no, you couldn't have guessed it because we didn't guess it. But I guess you could have demanded that there be something that was dimensionally correct, and so the dimensional correctness actually comes from the d of log k, as it written this way. So yeah, it's interesting. I don't know. I guess this is something that's puzzled me for a long time: is how long it takes a signal to fill out a cascade, and this is actually a clean derivation, which I had never seen before. There are a lot of implications for this, for adjustment of a turbulence cascade to variability and forcing and things. So this is a nice thing that I think will be fun to think about more. So so I'm glad that everybody got frustrated by this problem, and in the end, maybe we fixed it better than we needed to. So that's good. All right, so...
Sorry, Wyngaard.
Yeah?
I have a question about the previous exercise. How do we compute the time in the case of the atmosphere? Because I think it depends on epsilon and eta, or almost one of them.
Oh, so how do we get the time down here?
No, it's in the atmosphere exercise where we have small scale and large scale that behave differently. So one is 3-dimensional and the other is 2-dimensional, and it has, in the last part of the exercise, it asks us to compute the what's the name?
What the time scale is dimensionally.
Time of propagation of error.
Yeah, we actually have talked a little bit in the Thorpe problem about how you guess the scale for epsilon. So that's one way to get at it. But I think even if you just thought about writing it down abstractly, that would be helpful. But I haven't pushed through this result here, this 1176, into the dimensional form. But I will let everybody know when I post the corrected answer key, so you can take a look then. You have to estimate epsilon somehow, or eta somehow, and so you can do that by introducing some length scales and depth scales for either the atmosphere or ocean to get at those scales. So that's what I think is the intention for the next step. Or you can just remember that epsilon is order of 10 to the minus 7, watts per kilogram, and plug that in and see where that gets you to. Okay, so today we're going to talk about the atmospheric surface layer. And the main topic is really to start getting familiar with the Monin-Obukhov scaling. And we talked a little bit about the Monin-Obukhov scaling in, that's very funny, the money and avocado scaling is what it is coming in through in the captions. But it's not the money and avocado scaling, it's the Monin and Obukhov, two Russian names in that scaling. In Thorpe, basically, Thorpe just presents it as being, what do you do when you have both convection and surface stresses? And so we want to start to see how to think about that problem. And what comes into it is that you use the surface flux of heat and the surface stresses, and then some dimensional analysis, and you end up with much simpler equations that allow you to kind of think coherently about what happens in the surface layer under different limits. So we want to talk a little bit about that following through chapter 10 of Wyngaard. There's a lot more detail in chapter 10 than I think we really need to get to, so I tried to extract just a few essential pieces. So remember, if we're talking about an unstable boundary layer, we have the sun is coming in and heating the surface, which is driving these plumes. There's overturning, but there's also a background shear flow that sits on top of that. So we have both the surface stresses and we have surface heating together. And so if you think about the lowest layer that might be present in that case, this is what Thorpe calls the constant flux layer. Let's think about what the profiles look like. So we have the profile of the Reynolds stresses, we have the profile of the velocities, and we might also have the profile of heating, but the heating basically just matches the boundary condition and then heads upward. Those plumes would be transporting heat upward on average away from the surface. So the velocity might have some surface representation in one direction. That would be the wind speed at the surface. So without really losing generality, if we just choose that to be the x direction, whatever the direction of the wind speed at the surface is, then the u would have a profile something like this. It would have a wind speed at the surface, and then it would change as you go up to some different value aloft. The other component of the wind would be 0 at the surface, just because we've chosen to align our coordinate system that way. It would go to some value up aloft. And then here's where the interesting part comes in, is how the surface stresses balance out. So there's no stress in the direction of where there's no wind at the surface. So the surface boundary condition on the stress, and here we're thinking about the Reynolds stresses, but also the tau over rho, the u star squared, that part of it together. So this is the boundary condition, and then this is the turbulent flux, which has to match the boundary condition because you can't invent the momentum from nowhere. So the v direction, which has no velocity at the surface, also has no stress at the surface. The u direction, which has some velocity at the surface, also has some stress at the surface. And so you imagine having profiles like this that going from this matching value for the u direction up to some other value as you go up, and from 0 at the surface in the v direction up to some value above. So we can actually get more precise than this. We can try and solve for what the scaling for each of these goes, thinking back to our equations for the steady balance of a wind in the presence of a background pressure gradient. So steady, so we don't have any DDTs. We have FV, which is just the Coriolis term within the boundary layer. We have F minus VG, which is a way of writing the pressure gradient. That is what the geostrophic flow aloft would be once you've gotten away from the turbulence, and then the turbulence can come into this balance as well. So the deviation from the geostrophic flow is controlled by the divergence of the turbulent stresses. But if we go really close to the surface, we actually know what the turbulent stresses are going to be, and since this is a total derivative in z, we can actually do an integral over this. So if we do the integral over the v part, we do the integral over the u part, we can actually show that the u part, which is the stress, is going to be the integral of deviation like this, and the v part is going to be 0. So as we go from the surface up, then the net of the deviation from the geostrophic flow in the direction perpendicular to the surface stress should be 0. And the net of the stresses in the along wind direction, this integral, is going to equal the surface stress. So what this tells us is that if we were thinking about how big the UW might be, or how big the VW might be, we should use that surface stress and this depth over the boundary layer together to give a scaling relationship. So for example, this divergence, we don't really know what it's doing, but it's starting out at that value of u star squared, and eventually up here at some height, little h, where you're above the turbulence. If we drew a kind of triangle to represent that, we would say that this ddz of uw goes like u star squared over h. And then we could go back to this equation and figure out that what the balance is aloft. And so this is giving us scalings for how the pressure field and the turbulence go. This is a constant. This little h doesn't depend on anything if the boundary layer is stationary, which we're assuming it is here, in both space and time. And the stress is also, at least for the moment when we're looking, is a constant. It's an averaged quantity, and we're not imagining that the v or the u are evolving, so the stress is also not evolving. So using u star and h in this way, we get an equation like this, but we could integrate this equation too. What if we integrate this? This is constant, this is constant. We would find an equation that looks like this, where we have that the du dz doesn't depend on z, so the integral of this goes like z over u star, and so this being constant, that gives us a dependence on z only, and then this gives us this, and from this equation, going back to figure out how big the little h is, this tells us that if this is our definition for little h, the depth at which this holds for very thin layers right near the surface, whereas z over little h is much, much less than 1. So way below this depth where the turbulence vanishes up here somewhere, we would have this kind of a relationship for the stresses. Similarly, we could have done the same thing for temperatures, which when z over h is small for layers right near the surface, we could have gone through and come up with a temperature scaling. And the temperature scaling would depend on the surface flux, but little h and u star. And all of those are constants, at least under the assumption that this is a steady, statistically steady state for the boundary layer. So that's where the Monin-Obukhov scaling similarity theory takes off, is it says, what if we just think about all of those surface conditions that are steady for a statistically steady boundary layer, and use those as the scale parameters in a dimensional analysis sense for everything else. And so to list them more carefully, we have the length scale of the turbulence, which could be taken as the distance from the surface. So the biggest eddy, if we go back to here, the biggest eddy we might have is however tall our particular length scale of turbulence is. That's, if we were down here, we could only be thinking about eddies that would fit in between that z and the surface. If we were all the way up at the surface, we could have an eddy that was as big as that. If we were up at the little h up here where the turbulence dies, we can have z would be equal to h. So that's the sense in which we are thinking about the distance from the surface being the typical scale of the turbulence. And it's assumed to be isotropic turbulence, so the vertical distance from the surface is also supposed to be the scale of the eddy in the horizontal. The velocity scale, u of the turbulence, and since, as we just saw in that constant flux layer, the only dimensional scale that comes into the problem is the friction velocity, that surface stress condition. So that's something with the units of velocity. So if we take the velocity scale to scale with that velocity, then that gives us another set of dimension piece for our dimensional analysis, which is equal to the square root of the magnitude of the mean kinematic surface stress. We have the temperature flux at the surface, Q naught. And if we were thinking about a scalar constituent, we'd have also the flux of that scalar constituent in the surface, so maybe humidity could come in that way. And then the last piece, which is a non-trivial piece, is the buoyancy parameter, G over theta naught. And so G over theta naught, if we go, did I put that in our next slide? No, I did not. if we go back to our equations of motion, G over theta naught plays a special role because it's telling us how important temperature variation is. Here it is. So if it's that is in our equation of motion, that's the scale parameter that tells us how much momentum, vertical momentum, we get out of a temperature anomaly. So we need that key parameter. That's where the inelastic and Boussinesq equations really come in. So if we don't have that, we don't know how to relate the temperature equation to the buoyancy equation. And since we're thinking about convective turbulence, we really want to be able to convert between the temperature anomalies and their impacts on the vertical velocity scale. So we take those parameters, we put them together, and we think about how to do dimensional analysis. So here we have, so just reshuffling a little bit to remind us of some of the pieces. So we're thinking really about a virtual temperature. So we've got both a humidity part and a potential temperature part. And so this flux at the surface that we're thinking about, the buoyant flux at the surface, is a combination of those two. So it has the potential temperature flux in it, and it also has the moisture flux in it. This is the buoyancy contribution from a virtual temperature flux through the surface. So if we non-dimensionalize if we want to non-dimensionalize with U, we want to non-dimensionalize with this T star, which is just the flux of buoyancy, like this, divided by U star to give it the units of temperature. And if we've had another passive tracer, we would dimensionalize it with C, whatever the flux was of that, divided by U star. And now, if we count this up with Buckingham pi from all of these dimensional pieces, there is one more dimensionless constant. So this is a dimensional variable, dimensional variable, dimensional variable, dimensional variable. There should be one more dimensionless constant. And it takes a little algebra to sort out what it would be. But you can write it, or Monin and Obukhov chose to write it as the ratio of Z over L. This is dimensionless. And where L is, this part is not obvious at all, U star cubed theta naught over the Monin-Obukhov, the von Karman constant times G times Q naught. Why that is what it is isn't totally obvious at the moment. It's going to become more obvious as we discuss its implications. But this is the only dimensionless parameter. Here are the three-dimensional parts. And so it means that all of our solutions should only vary in the way that this parameter varies. So that's the important dimensional analysis part of this story. Okay, so here's the question. Is this L, looking at this formula, is that a positive or a negative quantity? What do people think? Exactly. Thanks, Akash. It depends on Q0. If Q0 is negative, then L would be a positive number. If Q0 is positive, then L would be a negative number. So let's think about that a little bit more. So L is negative in unstable conditions, but L is positive in stable conditions. And it's infinite Q naught when you have no surface fluxes. So there are kind of three conditions to think about. But the nice thing about this framing is if you think about the absolute value of Z over L, you're approaching a near neutral condition in this way that this dimensionless thing varies. So if this is a small, small thing, you're getting closer and closer to what looks like a neutral boundary layer. So the right implication of that is when we think about our constant flux layer is when you get really, really close to the wall down here, you are going to be able to treat it more and more like what you would have in the neutral case. So the thermal variations, whether they're stabilizing if the Monin-Obukhov length is positive and stable or unstable, right when you get near the surface, you're always going to come into something that looks kind of like the neutral case. And in the neutral case, we don't have to worry about the buoyancy effects, and we can actually just figure out, then we get our log layer and all the pieces of the story that we've talked about before in neglecting the buoyancy connecting to turbulence parts of this story. So when L is negative, it means that there is no height over the surface at which the turbulence is suppressed by the buoyancy effects, at least by the surface buoyancy effects. We know that eventually we hit a capping inversion or something like that, or the stratification of the interior, at which point we would have, the depth of the turbulence would go all the way up to where the inversion is. That was the case we were thinking about for the unstable conditions case. But throughout the boundary layer, L would not suppress any kind of turbulence, so that's the limit to think of when L is negative. But when L is positive, we would eventually, as we got away from the surface, get to a point where the stabilizing effects of surface cooling would rival the mixing due to surface stress-induced overturning. So then that would tend to happen when Z over L was order 1. So that's a nice limit as well. So this one parameter Z over L, think about it in negative and positive cases and zero cases, allows us to contemplate what's going on in the surface layer and deeper as we go into the mixed layer as we think about that part of the discussion. So here's another more less wordy, more mathematical way to think about it, is if we tried to think about what the shear profile looks like, what du dz is, we would scale that with K. So this looks like a log layer kind of approach where there's a du dz, a k, a u star. Instead of that being a constant, which is what we have in the log layer, or going to 0, I guess, that should be some function of this one dimensionless parameter. So if this dimensionless parameter was big or this dimensionless parameter was small, this kind of quantity, which is dimensionless because the units of big U over Z can only be canceled by little z over u star, and little z is, remember, our key measure of length, u star is our key measure of velocity, so this thing over here is dimensionless. And the way that dimensional analysis works is if you have no dimensionless numbers, if you have no dimensionless ratios, a ratio like this would have to be equal to a constant. And in fact, that was the case in the log layer. This was equal to a constant. What constant? The von Karman constant. But in the case where there is one dimensionless descriptor, so now Monin-Obukhov similarity brings in the surface flux of temperature, and we get one dimensionless ratio because of it. It's this kind of dimensionless factor is no longer a constant. It becomes something that depends on this other dimensionless ratio. So we have one dimensionless ratio proportional to another. The same thing would be true for the temperature flux. So the temperature the gradient in temperature from the surface would be scaled with u star and z like this, versus the flux. Any passive scalar would be scaled like this with z u star over c naught, and the von Karman constants here are for convenience, so that this thing has a value of 1 when you would be equal to the von Karman constant the way we would have in the log layer. Okay. So I realize that's a lot to say, but just look at what this tells us. Is if I knew this function, and this function has to be universal, at least when the assumptions of the MO similarity, that is, a spatially and temporally stationary Reynolds balance, like we assumed here. If these kind of flux balances occur, then the only show in town are these U star and H and Z and the Q naught and C naught. Once we have reduced our problem so that every kind of problem like that can be described with only those parameters, then every problem you can think about has to obey some kind of scaling law that goes like this. So this is kind of amazing because it says if I have an experiment with one L and an experiment with another L, I can relate them back to what the shear profiles have to look like this. Or alternatively, you give me one experiment that's carefully controlled, I can measure these phi m, phi h, phi c's, and then I would be able to generalize that to any other setting, regardless of what U star is, regardless of what Q naught is, regardless of what C naught is. So it gives you a way of generalizing the results from one experiment or a small set of experiments to a much larger group of implications. That's the power of dimensional analysis. Or I could measure these in the lab, and I can measure them very carefully. So the big experiment that Wyngaard talks about is the Kansas experiment, which was a boundary layer, very intensive boundary layer measurement experiment where they tried to measure all of these properties of the mean and how they varied as as day to night transitions occurred, and as different surface winds aloft changed, all that kind of stuff, in order to make sure that they had these functions figured out. A later paper reanalyzing those data and cleaning up some noise, this paper by Hagström, proposed these kind of simple forms for what these functions are. So let's look at them. So here's phi m has to be a function of z over L. Why not choose a linear function? Here are some dimensionless constants that are in that linear function. Here's the heat flux part. Here's some other dimensionless constants. And the reason why it goes to 1 here is because these von Karman constants are in here in the right way, so that that gives you a convenient value of 1 at z equals 0 is the right limit to get to, because of the von Karman constant was already built in. And in the unstable conditions, you see you have a very different functional form here. So the stable behavior has a generic result. The unstable behavior has a different generic result. And I thought I had the measurements that go under that. Go down and show what that looks like. I missed that slide. Oh, sorry. There's a nice picture. I must have deleted that slide by accident. There's a nice picture in the Wyngaard book that shows the kind of data that you would have that these kind of results might be extracted from. I can try and grab it. I'm not going to. But basically, it's just a curve fit. I mean, this is a universal function. What kind of universal behavior might you see? Well, whatever. You might be wondering why there are these very precise exponents. That's one of the pieces we want to talk about. Yeah. So one of the things you might, one of the applications you might think of this is, what if I wanted to know the surface stress with this complicated boundary layer, but I only knew surface stress, but I only knew the velocity at a particular reference level, the height of that reference level, maybe the roughness height that controls the log layer, the Monin-Obukhov length scale, and the background density scale. The dimensional analysis with the Monin-Obukhov assumptions in place would say that stress had to be some kind of function of only those parameters. There's no additional parameters that you could come in. So the new thing here is where I have the u velocity at a reference level and the z at a reference level. The other pieces are all just coming out of the Monin-Obukhov assumptions. And so you get a formula like this that says that I would get a drag coefficient. It's a tau over rho u naught squared at that reference height. What I'm looking for is a drag coefficient, the proportionality between those things. And that drag coefficient can only depend on two things. It can depend on the reference height that you're evaluating at and the reference height versus the Monin-Obukhov length scale. So if I know my Monin-Obukhov length scale, which I do because I can figure out what U star is from this relationship, I can figure out what the heat flux is because that would be specified in a model context, and I get to choose my Z reference level. That might be, say, halfway through the first grid cell in my atmospheric model. Then I can, once I know what this function looks like by comparing to observations, I could use this generically in any kind of application where I needed to know the stress from some velocity evaluated at a particular reference level. So this is the kind of thing that this approach makes very powerful. You can essentially derive the functional form of equations you might need. This is really a parameterization for the surface stress on the basis of the velocity, a known velocity at a particular height. You don't know what that function is, but you do know that at least it has to go like this. It can only depend on these two parameters. So then if you organize your observations or maybe boundary layer turbulence models to vary these two parameters, you would then be able to get, you could do a curve fit and come up with this kind of a relation. You would be able to extrapolate this relationship to a wide variety of applications. Let's talk a little bit more about how we interpret this L length scale. So we talked about it being the key distinction between, if it's really, really small, then we said that the convective forcing or the stabilizing forcing was negligible. But what happens when you're right where Z is about the same size as L? There's actually a nice way to think about that by just scaling for what the shear production should be and what the buoyancy production should be. If we take the scaling for shear production, it would go like U star times U star times U star over Z. And this one would go like G over theta naught times T star times U star. If we set these two terms equal to find out what height it would be, this one equals this one, that equivalent, the height of equality, just plugging in those two scalings for this one and this one like I just talked through, gives you this complicated formula. But oh, look, hey, that is in fact equal to the Monin-Obukhov length scale. So another way of interpreting when Z is equal to L is when the shear production is equal to the buoyancy production, or in the stabilizing case, when the shear production is equal to the buoyancy destruction. So if the shear production and the buoyancy destruction are equal at that height, you would think that that's the tallest scale of turbulence that could be fighting against the stabilizing stratification. If it was in the unstable forcing case, that would be the height at which you started to see the buoyancy production taking over from the shear production and producing the convective turbulence. So when you get up above that Z equals L level, you would have a bigger impact on those larger convective plumes, would be getting a larger fraction of their energy from the buoyancy production than they were getting from the shear production. And when you were closer to the surface than L, the shear production would be the larger source of energy for turbulence of that length scale L. You also can go through using the Monin-Obukhov scaling to estimate how big the terms we've neglected might be. So if it was an unsteady boundary layer, then you could, what's the time scale? How big is that time scale? How big is this term? You might say, well, it goes like a u, it goes like another u, and then there's a time scale. So what if we scale that as u star squared, each of those u's, versus that time scale, whatever it is? We could compare that to another term in the equation. So this one goes like u star cubed over length. This one goes like u star cubed over length. This one goes like u star cubed over length. This one goes like u star cubed over length. If these terms are really, really big compared to this term, then we would expect the budget to be steady. And so just by plugging in those scaling assumptions, we have a limit on what this tau u could be. As long as, so cleaning up the algebra on this inequality, for a given height, for a given u star, tau u needs to be small in comparison, or tau u needs to be big, I guess, to make this ratio small. This ratio being much, much less than 1 would predict that based at least on the shear production, the turbulent evolution time scale would be slow enough that we could neglect the steady part, the unsteady part. Similarly, we could do the same thing for a horizontal length scale. And now we're thinking about these terms when there's a horizontal length scale terms, and you end up thinking that basically the horizontal length scale over the vertical length scale, the vertical height that you're thinking about, has to be much, much greater than the mean wind speed over the stress friction velocity. So this is normally a pretty big ratio, that because the friction velocity is pretty small in comparison to u and under normal drag conditions. This side, that tells you how long your area of averaging has to be essentially versus the height you're thinking about. So thinking about this gives you a quantitative way of defining when you could essentially assume that the boundary was was sufficiently homogeneous over that length scale x, then you're in business. So these kind of relationships help you evaluate the underlying assumptions of Monin-Obukhov similarity. If these are violated, then you shouldn't trust the MO similarity to be enough of to be very predictive. So as we said last time, baroclinicity, if there was a horizontal temperature gradient and therefore a thermal wind shear within the boundary layer, that would set a new length scale. And so you could violate this kind of assumption by baroclinicity coming into play, which would essentially make the horizontal variations in the mean velocity big in comparison with the friction velocity. So we're going to see in submesoscale turbulence, that's exactly what happens, is we are thinking about length scales where the horizontal velocity is varying in comparison with the vertical velocity. So we lose the horizontal homogeneity assumption, and by a similar calculation, we also lose the time scale of separation assumption. All right. One of the things that we talked about last time was Richardson numbers, and we were thinking about those in terms of either the buoyancy force compared to the inertial force, or the buoyancy destruction versus the shear production, or the gradient Richardson number, which is the one that we talked about for Kelvin-Helmholtz instability. And so this was the key parameter in that dimensionless equations for the linear instability problem. But this rate of buoyant destruction compared to the rate of shear production, that sounds really an awful lot like what we just talked about here, the interpretation of the Monin-Obukhov length. So there must be some relationship between the Flux Richardson number and the Monin-Obukhov length. To put it a different way, in the Monin-Obukhov similarity theory, there's no room for another independent dimensionless ratio. So the Flux Richardson number shouldn't be an independent dimensionless ratio. It should somehow be a function of the Monin-Obukhov length versus z. And in fact, you can work through those relationships and show that the gradient Richardson number is exactly a function of z over L, and those functions that are deemed to be these are also functions of z over L. So basically, the gradient Richardson number is just a rewriting of z over L, some complicated rewriting, a polynomial kind of form, which is still a function of z over L. So the Richardson number is a function of the Monin-Obukhov dimensionless parameter, and similarly, the Flux Richardson number is also a function of the z over L's. And if you spend a little time thinking about what that means, it tells you that it looks like this, where you have phi m over phi h times the gradient Richardson number. So again, it's a complicated function of z over L, which is something that you could conceivably measure. So the Richardson number is not an independent descriptor of the boundary layer. The gradient Richardson number, the flux Richardson number are also predicted by the Monin-Obukhov scaling. And then the last thing that I was gonna talk about that's meaningful here is, even though these Monin-Obukhov scalings have in them the ability to simultaneously contemplate the buoyancy forcing and the stress forcing, they should have the right limiting behavior when you have very strong convection and weak stresses, or very strong stabilizing forcing and weak stresses. They have to have the right asymptotic behavior, so that when you try and converge back to the predictions for the surface layer, you actually get the right answer. And so without going too much into the details of that, how that logic goes, Wyngaard shows that this is true for the Monin-Obukhov scalings, and also uses it to predict the strong convective limit that should be seen as the limiting case, and the weak convective limit that should be seen as the limiting case. So basically, the small and large z over L limits get predicted by thinking about things getting independent of what's happening in the... So if you get up into the convective part that's just all convection and no stresses, there's a prediction by trying to remove U star from the equations. The equations should no longer depend on U star, they should just depend on all the other parts. And when you and so that gives you this prediction that the vertical variance of the let me think about how to say this cleanly. You want to show that things stop depending on U star, and you end up having equations where you're trying to cancel U star on both sides of the equation. It should be something like a constant times a function of U star for the things that are scaled by U star, or to put it another way, the Monin-Obukhov limit starts to govern the z dependence of the parameters without any additional dependence on U star beyond the assumed dimensional analysis. And you can do that for the strong case, and you can do that for the weak case, and that predicts these powers I have to give you in the limit of strong convection, and also those powers in the limit of stable stratification. So essentially, this is kind of the whole of Monin-Obukhov theory is a dimensional analysis on steroids. And so people have thought very deeply about this for a long time. We're going to have this to come back to when we do get to the kind of typical boundary layer conditions, but most of the parameterizations of boundary layer processes really rely on the Monin-Obukhov thinking. One exception to the rule that's worth pointing out before we quit is, what if we use the flux these kind of Reynolds stress budgets to think about when the unsteadiness term comes into bear by comparing it just to the turbulent, the shear production terms and the triple correlation product, all of which are supposed to scale the same way. But it is possible, and in fact it is not just possible, it is true in the real world that the pressure work terms, and indeed sometimes the Coriolis terms, and even if you have kind of a weird residual turbulence that has sort of kind of lingering viscous dissipation, come into play under kind of regime transition scenarios. What I mean by that is it is possible to generate unsteady boundary layers through a violation of the Monin-Obukhov theory, and frequently it's the pressure velocity correlation terms that are the actor of those kind of transitions. So this is very hotly being studied. This is an important part of lots of boundary layer extensions beyond the kind of Monin-Obukhov scaling, because people would love to predict these second moments. If you could predict the second moments cleanly, then you'd be able to write down turbulence budgets where you could solve for anything you wanted. But this term, these pressure covariances, tend to make that really complicated, and we don't have a good understanding of how to think about those terms yet. So that's where I wanted to stop for today. Are there any questions on that?
Sorry, could you just quickly go through the part you just said? I didn't fully catch that.
Yeah. So the covariance of velocity and velocity is scaled for very cleanly by the Monin-Obukhov theory, because it essentially has to, if I study an equation like this and I know how big this term is, I know how big this term is, I have to also know how big this term is. That's the kind of fundamental of the Monin-Obukhov theory. I could use that to estimate like the mean pressure gradient, which is really what's happening here. That's this geostrophic velocity is really a pressure gradient, but a large scale pressure gradient. So the Monin-Obukhov theory does really, really well predicting those large scale pressure gradients kind of by balancing them against other terms at different heights throughout the boundary layer. But if you try and determine other more complicated statistics in that flux and covariance budget, so this is the Reynolds stress budget. So we know how big this is because this is a term we actually just calculated. We know how big this is because it's a term that scales with the large scale pressure gradient or the stresses. We know, so there's not any complications in these ones, but in this triple product term, if it behaves differently from the double product term because there's some funny co-deviations in not the scale of U itself, but the scale of U, how it varies with other U. So like the phase of different variations in U. Or maybe it's easier to think about when you think about the pressure correlation term. So we talked about the velocity scale, but we don't know how the velocity correlates with changes in the pressure. So there's an unknown kind of alignment between variations in turbulent pressure and variations in turbulent velocity, or variations in turbulent velocity, velocity. So we've got kind of, multiple, turbulent phenomena. We don't know whether if we took this thing and raised it to the 3/2 power, would we get the same thing as this or not? So that kind of, that's something you can't get from dimensional analysis. So those covariances, those higher order statistics that are not predicted by the kind of assumed structure of the Monin-Obukhov are outside of what the Monin-Obukhov theory can predict. So what people are doing is they're taking turbulence observations and turbulence models and trying to understand how to extend this theory beyond the Monin-Obukhov assumptions. You know, how do we even think about how to quantify these other covariances and what do they depend on? We don't really know. So that's the point of like the last 3 pages of the Wyngaard chapter is going through that time and time again and kind of repeatedly saying that if we just knew how to do the pressure gradient velocity correlations, or you can write it also as a pressure strain rate correlation, you'd have a lot better sense of what's going on. Does that make sense?
Yeah, thank you.
Okay, great. So I will get written feedback to everybody about all the homeworks and update the answer key the rest of the way. And so we'll have all that stuff to discuss on Monday, and people can take a look. And when I post it, which will probably be sometime tomorrow or sometime Sunday, we will continue discussing on the next chapters, the next 2 chapters of Wyngaard. So if you want to read ahead, that will be really helpful in kind of solidifying this. Chapter 11, Chapter 12. And that'll be the task for the remainder of next week. And then we will be on to reading papers. I'll also, over the weekend, decide on an ordering of which papers we want to read about the submesoscale and the linkages between the parameterizations that are in active use in climate models and these theories that we've been discussing. So submesoscale, mesoscale, boundary layer turbulence, similarity theory, those linkages will be the topic for the remainder of the course. Everybody has already proposed to me what their final project is. I'll also give you feedback on that part. I'll be very careful to do that so that as you're thinking about how to optimize your time reading those papers, that will be as good as possible. But everybody I've had a conversation with so far about the paper projects seem to be right on track. So, great. Thanks, everybody. Have a good and safe weekend, and I will see you all on Monday.